Hey guys, Assalamu alaikum warahmatullah. Question number 3, chapter 24, electric potential. Figure shows 4 pairs of charged particles. For each pair, let V equal to 0 at infinity and consider V net at points on the x-axis. For which pairs is there a point in at which V net is equal to 0? Part A between the particles, part B to the right of the particles, and part C at such a point is E net due to the particles equal to 0. E net is the electric field. Part D, for each pair are there off axis points other than at infinity where V net is equal to 0. So we are given 4 configurations, 4 situations in which in each situation we have 2 charged particles, minus 2q plus 6q, here we have plus 3q minus 4q, here we have plus 12q plus q, and here we have minus 6q and minus 2q. We have to find out point on x-axis in between, part in case of part A in between the particles and part B to the right of the particles where net potential is 0, okay, where net potential is 0. Now, firstly, we know that potential is a scalar quantity, so we don't think in terms of directions. Okay, potential is a scalar quantity. Fine. Now, for net potential to be 0, since we are having in each situation we are having 2 sources for the potential. Okay, 2 sources for the potential. So, potential at any point will be potential due to charge 1 plus potential due to charge 2. Simply algebraic sum of the 2. And for net potential to be 0, V1 and V2 must be same in magnitude but must be of opposite signs, not of opposite directions, no, opposite signs. So one of them must be positive, the other one must be negative, and they must have same magnitudes, okay, same magnitudes. So we know potential due to a point charge is given by gamma q divided by r squared. Gamma is the electrostatic constant. Gamma q divided by r, not r squared. Gamma q divided by r. So it depends on the charge. It depends inversely on the distance from the charge. Positive charge develops positive potential. Negative charge develops negative potential. Remember, we need 2 potentials to be of opposite signs. That means we need 2 charges to be of opposite signs. Okay, we need 2 charges to be of opposite signs. In 4 situations, we are having, in situation 1, we are having 2 charges of opposite signs. In situation 2, we are having charges of opposite sign. Situation 3, same signs, so this is out of discussion. Situation 4, same signs, so this is out of discussion. So we are going to discuss it only for 1 and 2 now. So charges must be of same. Charges must be of opposite signs. Not only that, their values must be same. Okay, their values must be same. That would mean q1 divided by r, modulus of q1 divided by r must be r1. Let's write r1, distance from charge 1, must be equal to magnitude of charge 2 divided by r2. R is distance from R1 is distance from charge Q1, R2 is distance from charge Q2. So we need this to be valid. Okay, they must be of opposite signs. Fine. So considering that, we're reduced to 2 situations only now. Now the additional thing is that the ratio of charge to distance ratio must be same in the 2 cases. Magnitude wise must be same in the 2 cases, which means the charge that is having greater magnitude, the point must be also at a greater distance. The ratio will be same only if numerator is greater, then denominator must be also greater. If numerator is smaller, denominator must be also smaller. So that would mean if this is Q1 and this is Q2, this is Q1 and Q2, they are of opposite signs. Okay, they are of opposite signs, and Q1 is having lesser magnitude than Q2. Q1 is having lesser magnitude than Q2. If Q1 is lesser, then R1 must also be lesser. Then only the ratio will remain same. That would mean the point where net potential can be 0 must be closer to Q1, must be closer to the one with lesser magnitude of charge. The point must be closer to the charge The point where potential is to be 0 must be closer to the charge whose magnitude, whose value is smaller. So we have two things now. Number one, we need charges to be of opposite signs. We need charges to be of opposite signs. Then the point at which potential can be 0 must be closer to the charge with smaller magnitude. Okay, must be closer to the charge with smaller magnitude. So now let's analyze the situation. Remember, part A asks us whether it's possible for net potential to be 0 between the charges. Okay, between the charges. This situation is gone. It's not possible because charges are of same sign. This is gone because charges are of same signs. This situation, it is possible because one is positive, the other one is negative. In this situation, it is possible one is positive, the other one is negative. Okay, so in between the two charges, it is possible to have a point which is closer to the smaller magnitude. This one is the smaller magnitude here. So we can have a point which is closer to the smaller magnitude of charge. So potential can be 0 at some point between the two charges. Same is the case here. Smaller magnitude, 3q is the smaller magnitude. In between the two charges, we can have a point which is closer to the smaller charge. So potential can be 0 between the two charges. Okay, so potential can be 0. So potential can be 0 between the two charges in situation 1 and situation 2. So for part A, 1 and 2, 1 and 2 are the answers. Then part B, to the right of the particles, to the right side of the particles. Now remember, we have two conditions. Number one, charges must be of opposite signs. So these two situations are still out of discussion. Number two, point of concern, point where potential can be 0 must be closer to the smaller charge. When we analyze the right side is the side of bigger charge in situation 1. So we cannot have any point on the right side which is closer to the smaller charge. That point is always closer to the bigger charge. So we cannot have a point on the right side, in situation 1 where potential is 0, except at infinity, obviously. Okay, except at infinity, because at infinity we take that as a reference point. Potential due to this charge will be 0, potential due to this charge will be 0, so obviously net potential will be 0. We are talking about finite distances. Okay, we are talking about finite distances. You consider any point on x-axis that is closer to the bigger charge, that is not closer to the smaller charge. So potential cannot be 0 on the right side. Okay, potential cannot be 0 on the right side. On the left side, yes, it can be 0, because you can, we have a point here, in fact all the points which are closer to the smaller charge. So there can be one of the points where potential can be 0. Right side of situation 2, again you consider any point that is the side of bigger charge. 4q is bigger than 3q, that is the side of the bigger charge. So we cannot have any point which is closer to the smaller charge. So potential cannot be 0 at any point on the right side in situation 2. So for situation 2, none of the situations is possible. For part B, none. Remember, 3 and 4 are already out of discussion because they are of the same signs. Then part C, at such a point is E net due to the particles equal to 0. The point where potential is 0, the point where potential is 0, does it mean field is also 0? Does it mean field is also 0? No, it does not mean that. It does not mean that. If you remember, field in a region is, let's consider x-axis. So potential along x-axis varies like this. Okay, and field in a region is negative gradient of potential. We're talking about x-axis, so minus partial v by partial x. Negative gradient of the potential. Graphically, that is slope of the potential versus x graph. Now, if we consider this point here, potential is 0, but slope is not 0. Slope is not 0. We can draw a tangent here, not a very good tangent, but this will work. We can draw a tangent here. You can clearly see this slope of this tangent is not 0. So slope is non-zero, field is non-zero. So potential is 0, but field is not 0. Okay, potential is 0, but field is not 0. Okay, field is not 0. Then we have this point here where potential is maximum. If we draw a tangent there, you can clearly see slope is 0. So potential is non-zero, but field is 0. Okay, potential is non-zero, but field is 0. So we can have a point where potential is 0, but field is non-zero, and we can have a point where potential is non-zero, but field is 0. Okay, but there is a situation where potential is 0 in a region, not at a point, but in a region potential is 0, or potential is constant in a region. Then we can have field 0, but that is constant potential, or constant value can be 0 also, but in a region, not at a single point. Okay, not at a single point. So potential is 0, that does not mean field is 0. Okay, that does not mean field is 0. So what was the question precisely? At such points is E net due to particles equal to 0? Not necessarily. So no. Part C, no. Then we have part D. For each pair, are there off-axis points, so points which are not lying along the axis, somewhere up there or down here, are there off-axis points other than at infinity where Vnet is 0? Yes, there can be. Remember, this is not a vector quantity, this is a scalar quantity. So all we need is, we need two charges to be of opposite signs, and the point under consideration should be closer to the smaller charge. So we can have a point here, suppose, that is closer to the smaller charge. Okay, that is close. So potential can be 0. Okay, potential can be 0. We can have a point here, suppose, that is closer to the smaller charge. So potential can be 0. Not this one, not this one, because they are of the same signs. Okay, so yes, it is possible in situation 1 and 2. 1 and 2, it is possible, not in 3 and 4. Is that fine? Had it been field, talking about the field, can field be 0 off the axis? No, because field is a vector quantity. You have to consider directions. For net field to be 0, due to two charges, two fields must be of opposite directions. And off axis, two fields cannot be of opposite directions. Negative charge field will be this way, positive charge field will be this way. They are not in opposite directions. So in case of field, no. But in case of potential, yes, that is possible. Okay, that is possible. So that's all that was asked in this question. That'll do for this session.